Hello and welcome to today's video. Today we're going to look at limits. For some reason my title's not working there. Okay, so let's leap straight in. Okay, so the big idea today. So limits, well, basically we're going to look at limits all the way through this semester. What happens to a function as we get close to, but not necessarily at, a particular value. So those help us, and we'll see this as we're going through, thinking about change, velocity, tangent lines, continuity, all kinds of things. Okay, so we'll start by asking actually what's kind of a simple and slightly silly question, I suppose. What happens to sine x over x as x approaches 1? Okay, so we have a function, we can approach 1. So let's take some values that approach 1, and we're going to approach from the positive and the lower side, the negative side if you like. So on the left-hand side there, you can see we get 0.5, 0.9, 0.99, 0.999, so those values getting very close to 1. On the right-hand side there, we approach 1, but from the other side, so 1.5, 1.1, and so on. And it looks like that's approaching about 0.84, maybe 0.841, maybe halfway between those two values. But of course, this function at 1 isn't very complicated. We could just plug the number 1 in, and sure enough, we plug in the value 1. We just get 0.841471. So that's certainly what it appeared to be approaching with the limit, but there's nothing very clever about that. We could have just put the value in to begin with. So instead, let's ask a different question and a more interesting question. What happens as x approaches 0 to this same function? So notice now, sine of 0 is 0. Obviously, if you plug in x to 0, it's also 0. So this fraction is 0 over 0. Okay, so we can't just plug the number in. I don't know what we get if we just plug in 0 over 0. So now maybe it makes more sense to take this limit, these values. Okay, so again, we'll approach it from the sort of positive and the negative side. So 1.1, 0.01, 0.001. And then from the negative side, negative 1, and same on the negatives here. And sure enough, it looks like as we approach that, we're approaching the number 1. Okay, we get 0.999, I think it's like 6 nines there. So it appears that as x approaches 0, sine x over x approaches 1. So that's what we mean by a limit, even though the sine 0 over 0 is not defined. Okay, and this is kind of the key point, probably for the whole class really. If we have a graph of this function, you'll notice we have kind of a little hole here at 0, 1. And the point being that the limit can exist even if the function doesn't have a value at that point. Okay, so the limit of the function is 1 even though it's not defined at 0. Okay. And that's probably the key point about these limits. Okay, so let's try another example. Let's take x cubed minus 2x squared minus 5x plus 6 over x cubed minus 4x squared plus x plus 6. And we're going to take that as x approaches 3. And you can plug it in. Maybe you just have to trust me that if you plug in x equals 3, this becomes 0 over 0 again. So again, we have the problem. We can't just plug in the value we're interested in and get an answer because it's undefined at that point. It's 0 over 0. But this time, rather than just plugging in numbers, which we could do, let's try and be a bit clever. Okay, so we'll notice that that trinomial there, that x cubed function, factors. And again, don't worry about how we factored that right now. Let's just trust that it factors. And we'll notice that when we factor it, we get an x minus 3 in both the numerator and the denominator. And that shouldn't be a surprise because if we plug in x equals 3, we get 0 and the 0 here. And that's what's causing it to be 0 over 0. And so from this, well, we can just factor out. We can just cancel the x minus 3 and the x minus 3. And as long as we're not actually at x equals 3, we can cancel those out and we just get this. And once we've cancelled those out, well, we can just plug in x equals 3. Well, figure it out, point in the values. And if we plug in x equals 3 here, we get 5 over 2. And sure enough, that is the limit. So if we can cancel out the things that are sort of creating that 0 over 0 effect, then it's easy. Then we just plug in the value we're interested in, and in this case, we get 5 halves. Okay, so limits. So far we've just talked about a limit approaching some value. First we'll introduce some notation. So we see this x approaches a, and then we have this kind of superscript of a negative. that means it's approaching the function from the left-hand side, or the x value from the left-hand side. And here we're approaching a from the right-hand side. That's what this plus means. And so I say from the left here, and from the right here. And in this case, the function is approaching two different values from the left and the right. And in fact, that's an important test for us. The limit itself exists if and only if the limit from the left and the limit from the right are the same. So if the limit from the left and the limit from the right are both L, then we can say that the limit over all is L. If the left and the right limits disagree, like they do here, then we would say that the limit does not exist. We can't say there's a limit here. A left limit and a right limit, but not a limit overall. Okay, and then a couple of the types where the limit doesn't exist. So we have to be a little bit careful here, because there's kind of two different cases, and they are slightly different. If we approach 0 from 1 over x squared, well, the limit doesn't equal a finite value, but we would say that the limit equals infinity, right? As we go up here, we're going towards infinity. So we could say the limit equals infinity, but obviously that's slightly different than a finite number. Whereas on the right here, from the left, it's approaching positive infinity. From the right, it's approaching negative infinity. So then we would definitely say the limit doesn't exist. Now we're back to this rule again, that if it approaches something different from the left and the right, then it doesn't exist. So again, let's take a piecewise function, for example. So this function is going to be x squared minus 2x plus 3 for x less than or equal to 1, and x for x greater than 1. Again, it approaches something different from the left and the right. Therefore, the limit, so here, from the left it approaches 2, from the right it approaches 1. But so overall, this limit as we approach 1 doesn't exist. Okay, one more slightly funky case, but I always think it's kind of cool and fun to see the drawing. Cosine of 1 over x as x approaches 0. So what the heck is happening here? Well, as x approaches 0, 1 over x is going to infinity. But if we think about cosine x as x goes to infinity, it just keeps oscillating. It'll keep oscillating forever. We know that cosine goes up and down forever. But that up and down forever has to be kind of squashed in here as we approach 0. So although it looks like it stops here, this actually will just keep oscillating forever and ever and ever. Okay, so we would also say that limit doesn't exist. Okay, so now we're back to things kind of related to what we looked at on the first day. We're going to take our displacement, our position, to be this t squared over 2, and we want to ask what is the velocity at t equals 2. Okay, so just like we saw in the previous class, rather than taking it at 2, because I don't really know what to do there, let's take our average velocity from 2 to another point in time. So just for example, if we're going from 2 to 4, our position at 2 is 2 squared over 2, which is 2. Our position at 4 is 4 squared over 2, which is 8. So 8 minus 2 is 6. It's taken us 2 seconds, or whatever the units are here, to go 6 units of distance, so our average velocity is 3. We can do exactly the same thing from 2 to 3, 2 to 2.5, and again we're taking this, getting closer and closer to that 2, and as we look at what the velocity says to be approaching, well, that appears to be approaching 2 as well, right? 3, 2.5, and so on. It would appear that our velocity is approaching 2. Okay, and then we can go back to kind of the stuff we were using previously. Y of 2 plus h minus y of 2 over h. Plug that into the function, do some algebra, and obviously I'm racing through this a little bit, but you do the algebra to the point where this 2 and this 2 cancels out, and once the 2's are cancelled out, the h's also cancel out, and we're left with this. And once we've reached this stage, we still need to take the limit as h approaches 0, but it's no longer a problem. Like if we did it here, we get 0 over 0 again, but if we do it here, well, it's easy, it's just 2. The limit as h approaches 0 of 2 plus some h over 2 is just 2. And of course that agrees algebraically with what we got numerically. Okay, so we're covering a lot today, so now we're going to leap to continuity. So definition, function is continuous at a point c if the limit at c is the same as the value of the function at c. Okay, so we need kind of three things for this to be true. First, that the function is defined at that point. Second, that the limit exists at this point. And if both of those things are true, that both of those things are the same. So the limit and the value of the function are the same at that point C. Okay, and then we can have a few different types where we don't have that occurring. My circle's a little off here, but imagine this hole is on this graph. That's a removable discontinuity. Okay, you might want to call it a hole discontinuity. If we have a hole, we have a gap there. So that's a discontinuity. We have a jump discontinuity, so we jump up here. And then finally, we can have an infinite discontinuity, which we saw previously. The function's going off to infinity. So these are the sort of the three main types of discontinuity we can have. Okay, so let's look at the removable discontinuity. Remember, that was the one where we have kind of the hole on the function. So we're going to take this function, x squared minus 3x plus 2, x squared minus x minus 2. And we're going to plug in, well, we're going to be interested in the value 2. So at the value 2, this is 0 over 0 again. So it's not defined at that point. If we just go back to our rules, we've already failed this rule here, right, that it's defined. But we can factor this. So just like we did previously, we can factor the x minus 2 and the x minus 2. And so the limit as we approach 2 is 1/3. And we have this case where the limit equals a finite value, but the function itself is undefined at that value. That's what we call a removable discontinuity. There's a hole in the graph there. Okay, so it's often these kind of 0 over 0 cases where we can factor out and make it go away. That's removable. Okay, so the step functions. So this is a common case of the jump discontinuity we talked about. So a step function, so the floor and the ceiling function. So the floor function is just literally round down to the closest integer. So if you have the number 3, you round down to 3. But if you have the number 3.1 or 3.9 or 3.86 or even pi, the floor function of that would just be 3. Similarly, the ceiling function of that is round up. So we have the number 3, it stays at 3, but 3.1 would go to 4, 3.2 would go to 4, even 3.01 would go to 4. It's round up to the next integer. And so at each integer, the one-sided limits would disagree. So I guess this particular one is the floor function. So any value between 0 and 1, we round down to 0. Any number from 1 to 2, we round down to 1. And so that means that every integer, let's take 1 for example, from the left we approach 1 and we get 0, from the right we approach 1 and we get 1. So this is again a discontinuity, and in particular a jump discontinuity. Okay, so of course we spent a lot of time looking at where things are discontinuous, but often things are just continuous. So for example, we take a polynomial, 3x squared minus 5x plus 6, it's just continuous everywhere. Any number we could put in would be continuous. A rational function, so that's like a polynomial over a polynomial, that's continuous wherever it's defined. So basically, as long as the denominator is not 0, it's defined. So we go back, let's look at the rational function we had a second ago. So here, if we plug in 2 or negative 1, it's undefined, so it's discontinuous, but everywhere else it's continuous. So any other number except for 2 and negative 1, this function would be continuous. And actually lots of things are continuous most of the time. Polynomials, rational functions, etc. They're continuous as long as the point is in their domain. Okay, so for example, let's take this function. This is continuous as long as x is not 1, because if it was 1, we'd get a 0 in the denominator here. And anything 0 or less we can't have, because it's not in the domain because of the log x here. But it is continuous everywhere else. So it's continuous from 0 to 1, and from 1 to infinity, so the union there. Tan x is continuous everywhere except for, so if you're familiar with the graph of tan x, it has these kind of infinite points of pi over 2, but also 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. So it's continuous as long as it's not at those points. Even this, square root of 4 minus x squared. Well, we can't define this. If we take x to be, whatever, 50, we'd have a negative inside here and we can't do it. But anywhere between minus 2 and 2, this is continuous. And we can actually include the endpoints here, the minus 2 and 2 here. So this is continuous all that way. Okay, so that's a lot. We've covered a lot today. But let's think about what we need to remember. So the limit describes what happens to the function as x approaches a value. And that limit can exist even if the function isn't defined at that point. The two-sided limit exists only, and only if, both one-sided limits agree, so it approaches the same thing from the left and the right. And our function is continuous if the limit of the function equals the value of the function. Okay, so I'll say that was a lot, but I think we've got it all covered. Thank you.